Yeah, I'm going to try to keep doing this in all my classes. I started doing it last semester because I had a student that was really seriously ill.
Yeah, I actually heard about that.
Yeah, and you know, to accommodate that person, I started doing this, but then I realized, you know,
It's
that
not that much extra work.
exactly, people really, a lot of people other than her use the video. So.
Maybe even people not in the class.
Yeah.
Yeah.
Plays into your whole like open source.
It does.
Thing
Yeah.
really well.
Yeah.
I had a quick question.
Yeah.
So there's two functions in the list class that have const keywords to prevent you from changing the
Yes.
arguments. One of them you pass in the list error e. One of them you don't.
Yeah. One of them returns a pointer. And the error, the way that the error is transmitted back to the user is you get a null pointer, and then the other one I think is void, and the way that you transmit the error back is through E. That's why I did that.
Okay.
I don't remember exactly which ones there are, but I think that was.
The one where you send back a null pointer.
Yeah.
I put const in the header file, then put const in the.
That's right. In the implementation. Yep.
And it was fine.
Yep.
The one where you're changing the value of e, const in the header file, const in the definitions file, didn't work. Said the functions didn't match. Delete the word const in both of them, it works.
I mean,
That's the one where you're trying to change the error message.
I got it work pretty.
See, but a const member function should be allowed to change an argument that's passed by reference. It's really just designed to assure the programmer that it's not changing any of the private data.
Are you sure the consts were both in the same place, like preceding the function, or well, actually it doesn't matter whether they're preceding or after, but they can't be an argument const.
Right, they're both after.
I'll check afterwards and see if there's some kind of weird syntax error, or maybe there's something. I'm pretty sure that I'm using that and using it without a programming error, without a compiler error.
Okay.
So check with me afterwards, and we'll just look at your source code. Today we're going to start talking about stacks. Let me see here. I'll talk. I have a brief comment about the list class. We're going to start talking about stacks, and we're going to talk about how you might implement stacks in various ways. And then what I'd like to do is spend some time talking about what are some of the things that you have to do when you have a class that uses dynamic memory. C++ is not a programming language for the faint of heart. It's a production level programming language, has a lot of sophistication built into it, and we're going to really start diving into some of that sophistication today in the form of what are called copy constructors and assignment operator overloads. These are two features of the language that are incredibly important for classes that have dynamic memory, like the list class and like the stack class that I'm going to have you write next week. So before I get into that, let's. Oh, yeah, and I wanted to talk about the list class a little bit. A couple of you, and frankly, I might have done it myself in just sort of a slightly alternate universe. A couple of you have added a size variable to your list class that you just keep updated, like when the constructor sets the size to 0, every time you insert an item it increments size, every time you remove an item you decrement size, and that way you have it there whenever you need it in various member functions. If you want to do that, that's adding to the class. That's not going to get in my way at all. So if you want to add a size variable to the private section and keep that updated for your own purposes, I'm totally fine with that.
What about using it to cheat and writing all of our member functions?
Be more specific.
Well, last is a lot easier because then you just do get. You just write get node, and last becomes get node like -1.
Or.
But you still have to traverse the list.
Yeah,
that's not cheating to me.
Well, like checking your insert cases becomes a lot easier.
Exactly, which is one of the reasons why you might want to do it.
Okay, so cheating is okay.
It's not really cheating. I mean, it's
anything you can do to make your code easier.
Right. I mean, the only
Well, I found this online. I copied and pasted it.
Yeah. Let's not make it that easy. So yeah, if you want to do that, feel free. So today we talk about the first. A linked list is by itself not really a data structure. I mean, it is and it isn't. The first real data structure that we'll talk about in this class is the stack. The way to think about stacks. Gosh, I don't know if you guys have any of these in like the dining halls, but you've probably been to cafeterias where there's like a bunch of plates and they're in a hole, and you pull one off and then they rise up and you pull another one off, or you come in and you shove the plates onto the stack. Like if you're the dishwasher and you've got a whole new stack of plates, you come in and you shove them into that's a stack. Okay, there you go. That's a stack, and the primary feature of a stack is that it's a list of items that follows a last in, first out protocol. The last guy in is the first guy out. So let me write some words up here, and then we'll talk a little bit about what these things are actually useful for. This is a list that is known as a last in, first out protocol. And you will often see this in the literature abbreviated as a LIFO. And you'll also see FIFOs, first in, first out. LIFOs and FIFOs. So stack is a classic example of a LIFO, last in, first out. Some applications. Probably everyone in here has used a stack unwittingly when you do Control-Z in Word, for example. What does Control-Z do? Undo. So what happens is Word kind of keeps track of all your activity, and maybe not every little tiny little atom of what you're doing, but it sort of has built-in thresholds for what it considers an event. And when it detects one of these events, it takes that event and it pushes it onto a stack. And it just keeps watching what you do and taking these events and pushing them onto the stack over and over and over again. And you hit Control-Z, and what it does is it takes that event and undoes it and gets rid of it. And then you hit Control-Z again, and it takes that off and gets rid of it and takes that off. And that's a last in, first out situation, right? It's not technically a stack because, as Ben pointed out to me last time, I think, what was it, Control-Y? Yeah. Goes the other way. So a stack would literally take that top item off and throw it away. You would never see it again. What Control-Y does is it lets you grab that thing and put it back. I didn't mean to get rid of that. And so what you're really doing is moving back and forth in a list of events that Word is keeping track of. But I think it's good to think of it as a stack in this particular case. Control-Z in Word, the undo command. The big application that you're going to become really comfortable with is evaluating expressions. Using things like parentheses, addition, subtraction, multiplication, division, and whatever other operators you might find interesting. We'll talk more about this later, but that's going to be the big application that we use to really explore stacks. What I'm more interested today is not the applications of stacks, but the implementations of stacks. How are you going to write a program that implements a stack so that you can then use it to evaluate expressions or do undos or things like that? So, implementing a stack. Implementation. All right, a stack is a list. and you add and remove from the front or at the front. So this is actually a lot simpler than what you're working on right now. Simpler because if you want to push something onto the stack, it goes on at the front. If you want to take something off the stack, it comes off the front. And that's it. And then the rest of the stack just takes care of itself. Two ways of implementing this, well, several ways of implementing this, but two primary ways. You can store the information either in an array or in a linked list. Each has its advantages and disadvantages, but linked lists, if you have sort of a fixed size, if you have a fixed number of items or a maximum number of items, then an array-based implementation might be fine. And here, if you have an indeterminate number of items, then a linked list might be appropriate. All right, let's look at some of the operations. So let's talk about an interface for a stack class. So what are some member functions that you would want in a stack class? What are some things that you would want to know about a stack or want to do to a stack? Okay, so we want to add an item. This is typically called push.
That word push back comes from the vector. Just that adds it to the back.
It does, yes. So we add an item to the stack. What else? It's actually pop, but pull, I appreciate the symmetry there. That makes sense. So pop, what do you mean by pop? Yeah, so that would be removing an element from the stack, right? What else might you want to know? Yep, that's typically size.
And the theory about putting that in a function instead of just making it a public variable is that they can't mess with it, right?
Yep. Yeah, so size would be a constant member function. It would tell you what the size is, but it would not let you set it. And you certainly don't want to muck around with the size, right? You would break the object if you changed its size and didn't change the number of items in it. So that's sort of the whole foundation of the public-private paradigm. Is you don't want the users of your objects to be able to muck around with the internals, because if they don't really understand how you're implementing your class, they might break the object and get unreliable results. What else might you want to do with this thing?
You need to create something specifically, because you said once you pick it out, it's deleted from. That might be internal to pop or something. But peek.
You could peek. I will say that we're very nearly there with these three and one more. Typically, a stack has an empty test. I don't know why, but they'll have that in there. This is a Boolean, and it's true if empty. But that's really redundant to size, right? If size is 0, you get the same thing. But yes, Josh just mentioned peek. Some people call that top, and this is it returns the next item on the stack, but leaves it there.
Why is it called top if it just goes through? Well, because like, I mean, it just seems like top would just return like the top thing on the stack.
That's exactly what it does.
Oh.
Yes.
Okay.
But it leaves it there as opposed to pop. Pop typically does not return a value. Again, there are lots of different ways that people implement stacks, but typically pop won't return a value. It'll just literally remove the top item, and you don't know what it was. So often you'll separate pop and top. So you'll do top and then you'll pop. If you care about getting that information off of the stack, yes.
So then, just using these, we don't really have a way of looking at the whole stack while preserving the stack.
Right.
We would have to sort of create a new stack and bump stuff over there as we pop through.
So if it's important for you to know the contents of the stack at a particular time, then you're right. What you would have to do is add a member function to your stack that gives you more random access to the stack. But then you're kind of away from what a stack really is. So this is it. Stacks are not that complicated. You mess around with one end of the stack. It's probably a relief compared to what you're dealing with right now. So there's a standard interface. Let's talk about internal representation or internal storage. And let's talk about the array-based version first. So if you're going to do an array-based implementation, think about how you want to do these various actions. For example, you start out and you have an empty stack, and that's just an empty array. And for definiteness, let's just pretend that we're dealing with an array of integers. We're pushing integers onto a stack. We're pulling integers off of the stack. That's pretty simple, right? So in the private section of your class, you're going to declare an integer array, and maybe it's size 100 or something like that. Okay. So for definiteness, let's just say int a 100. What else do you need in the private section here? Size. Well, to be honest, for me, empty is going to return true if size is 0. Yeah. Okay. Is this enough to represent everything about the stack?
Well, you have to decide whether you're going to start, have things pop off the end.
Yeah, so now we're getting into how you would actually write push pop size empty and top. But what I care about right now is the data of a stack. Can we learn everything we need to know? Can we do everything we need to do with this data that we have right here? A100 and size. Within limitations, we can't have a stack larger than 100 elements. But yeah, everything that we need is here. Let's talk about what Ben was just talking about. Actually, no, before we do that, let's talk about linked list based.
There's also the issue with this one. You have to somehow make sure you don't skip the space like a linked list or maybe like you because you can't like have a weird empty spot. But
we'll talk about that. In a linked list based situation, what kinds of data do I need in the object to keep track of the linked list version? We can say the nodes are, we have nodes, but I agree with you. So I'll just put parenthetically here, we need some nodes of some kind. Now that we have nodes, what's in the private section?
Size.
Do we need size?
You don't need it, but
Well, you need it in array-based.
right.
Do you need it in linked list-based? No. So what do you absolutely have to have?
Head.
Head, exactly. You need a node star. And that's pretty much it. How do you know that you're at the end of a list, or how do you know how big a list is?
Just count through it.
You go through it and count. And when you get to the null pointer, you know that you're at the end of the list. How is that different from array-based?
You can't go through an array unless you know how big it is.
Yeah, you just don't know what the last element of the array is. There's no signal to you as you go through the array that says, oh, there's only 47 elements in this array. Right? Because the 48th element is just going to be some piece of memory out on the system, and there's nothing special about it. So linked lists are a little different from arrays in the sense that they have this natural, as long as you're keeping the pointers pointing at null appropriately, you have this natural signal at the end of the list that says, hey, you've reached the end. That said, I would have a size. It's more efficient. Because otherwise, every time I'm asking if it's empty, or maybe not empty, every time I'm asking for the size, I have to do a traversal. That's really annoying. So this is more efficient because it avoids unnecessary traversals. Okay. Now let's talk a little bit about implementation. And we'll just sort of sketch out, let's talk array-based first. And now we're ready to address some of Ben's comments. Array-based. So let's talk about broad strokes first. How do you want to run this stack in an array-based representation? Where do you want to put the next item?
0.
So you put the first item at 0. Where do you put the second item?
0.
What do you do with the one that's at 0? Really?
Won't that require you redefining the array?
What it's going to require me to do is slide it down and open up a spot. So,
Size.
eh.
You're wrong. Start at the end. Count -1, size -1.
So think about it this way: you've got this array. You throw the first element into the 0 slot. You throw the second element into the 1 slot. The third element into the 2 slot. Now you're going to pop. Just pop it off at the end, and now you're back to the first one. Now you're going to push. So you put one back in there. Put another one, and you just keep going out, in and out like this at the end of the array. So even though you're always putting things at the front or the top of the stack, in the implementation, you're really adding stuff at the end of the array to avoid sliding stuff down to make room at the front.
So you have some, don't you need, or I guess size functions is like an index pointer, right? Not actually a pointer, but.
Yeah, let's talk about that. So just let's make a comment here that we're always going to be adding and removing from the last index. Okay. And just to make it clear, as opposed to the 0 slot. Because this avoids lots of unnecessary copying. So we add and remove from the last index. We actually know precisely which slot to put the next guy.
Yeah. Well, that's the
It depends.
Well, if you start indexing from 0, and let's say you have 0, 1, and you say size is 2, then you put it in at size.
So you put it in at size, and then what do you do to size? You increment it. And if you do that, you're fine. Don't increment and then put it in. So yeah, absolutely. You always add the next item at size, and then you do size plus plus. So in fact, what we know from this is that the last element, or the top of the stack, is always where? Oops, size minus 1. The top of the stack is always at size minus 1. So for example, if I ask for top, what is top going to do? The member function. It's just going to return the array, the elements at size minus 1. What's pop going to do? It has to even do less than that.
Size minus minus. Yeah.
Size minus minus, walk away. Okay, you don't actually have to get rid of it. By decrementing size, it's still there, but it's no longer part of the stack. In fact, that's likely what's going on inside Word when you do undo and redo. You're just decrementing and incrementing size, right?
But then what about the fact that if you like undo something and then type something?
Okay, that gets more sophisticated, right? And frankly, I haven't explored the undo redo features of Word. It's not my word processor. But what you do, and in fact, some of the browsers have this issue too, the back button and the forward button. So you go back a couple, and then you go somewhere else that's not the same as where you just were. And what you do is you create a branch. And some browsers actually have tree-based histories that let you move around in the tree. So I go back a couple, and then I go down this other branch, and then I can go back a little bit, and I can go back down the other branch if I want. Of course, this really gets complicated when you have multiple tabs in a browser, each carrying around its own history. So it's a hard problem if you think about it. All right, so the top of the stack is always at size minus 1. And I think you get the idea about how to do some of these other ones. Push, size is easy, empty is easy. So I think the array-based implementation is pretty straightforward. People have a pretty good idea of how that's going to work. Let's talk about the linked list implementation. All right, linked list. How do you add a new item to the stack?
Make a new node.
Make a new node, and where do you put it?
After head.
I think it should be head.
Yeah, it's at head, at the head.
Right. So head points to.
Yep. So head points to the new node, and the new node points to the previous head. Right? This is much more in line with what Evan was talking about with the array-based. That makes more sense. Like I'm adding at the front. Why am I not adding at the end of the linked list and removing from the end? Because I'm doing unnecessary traversals. So it's kind of interesting. These two representations are kind of complementary. There's sort of you naturally want to work at the end of an array-based implementation, and you naturally want to work at the front of a linked list implementation. So you do a new node. So you insert a new node at head, pop, you remove the node from the head, and all that sort of stuff. So I think you get the idea. You're always working at the head node. And then if you have a size variable, you're keeping track of that separately, incrementing it when you're inserting stuff, and decrementing it when you're removing stuff.
This isn't totally related, but is it computationally more intense to work with an array or a list-based thing if you're removing things from the middle? Like, is it easy for the computer to get an item in an array, or to look at the pointer and then go to that pointer and look at it?
If I'm removing stuff from the middle, is that what you said?
Well, yeah, but I guess I'm just wondering in general. So like the reason that we use like a list is because it's a lot simpler to delete like something in the center and just move the pointers around.
Mhm.
But is it more, if all you're doing is like looking at a long list, is it harder to go through a linked list?
It's harder to go through a linked list. If you have a static array like the one I've just written up there, most of the time, in fact, almost 100% of the time, you can rely on what's called contiguous memory. So the compiler, the writer of the compiler, and the operating system have all kind of implicitly guaranteed that 100 element array of integers is actually 100 or 400 consecutive bytes in memory. What that lets you do is something called pointer arithmetic. So the name of the array is actually a pointer to the first byte of this chunk of memory, and then I can actually advance that pointer using pointer arithmetic, and it's very efficient. It's really leveraging the operating system to get at random access memory, and it's about as efficient as it gets. So if you want super speedy code, what you do is you try to use static arrays and pointer arithmetic, because I know I'm going off on a tangent here, but if you have a two-dimensional array, say int 100 100, it's still better than like a two-dimensional linked list, whatever that is. I mean, they do exist. It's doing it this way is still better than a two-dimensional linked list. But what's really going on here is, let's see, C is a row major storage operation. So what it'll do is it'll take the first row of this, so A00 through A099 are all in this one long line, and then A10 to A199 are the next, right? And they're all in this one long line. To get to A25, the compiler or the program is actually going to do 2 times 100 plus 5. It's actually going to do that little calculation, and then it's going to advance the pointer out to that row and then that element in that row. That's actual floating point computation that can be avoided if you simply start at the front and add whatever I said, 205 to the pointer. If you take that pointer and you advance it 205 integers, that's going to be more efficient than doing A25. Because when you do A25, you have this extra multiplication in there that's not present if you just go directly with. And people that write high performance, super high performance numerical computations, they avoid using these two-dimensional array indices, because hiding in there is a multiplication that you might not want. Yes?
Is that like a new pointer? So you just have, have this pointer and then you have.
It's not a new pointer, like
Okay,
you,
so then
unless you explicitly store it somewhere.
Right. So
Yeah.
then do you effectively lose the other part of your array?
No, because A here, A is an unusual kind of pointer in C and C++. It's not quite a pointer, but it acts a lot like one. And you won't lose A by adding stuff, right? You'll get a new pointer out to new memory, but A is still there and you haven't lost it. And it still points to the first element, the first byte of the first element.
So how would you access A? Like the pointer form.
Right, so you do, for example, if you do star A, that dereferences A, and it's going to give you the first integer in the array or the first float in the array. And if I do star parenthesis A plus 1, it's going to give me the next element in the first row. And star parenthesis A plus 200 is going to give me, let's see, there's 100, 200. It's going to give me the first element of the third row. This is totally aside, but it's really cool, the kinds of things that people do to avoid evaluating these things. Now, that said, I'm kind of dating myself. I strongly suspect, it's been a while since I've done this level of computational efficiency, I strongly suspect there are now flags to compilers that will just automatically do this stuff if you care. So it'll turn all of the AIJs into pointer arithmetic and avoid the multiplication.
At the compile
At the compile step. It'll rewrite the code so that it uses pointer arithmetic instead of dereferencing. Okay, moving right along. We are going to write, so next week and possibly even into the following week, we're going to be writing a linked list based stack implementation. But before I go there, I want to show you, remember back in calculus when you had to compute the derivative using the definition? And then they come along and they say, oh, just do this, right? And you're like, grr, I'm about to do that to you. Because these data structures are really important, and they're so important that they already exist in C++. So you can just include stack at the top of your program, and then you can declare a stack and you can use it. But I'm not going to let you do that. You're going to write a stack.
Is there a linked list implementation already as well?
Well, that's the beauty of it. We have no idea. I mean, we do have an idea, but as the user of the stack STL, you have no idea, nor do you care how it's being done internally.
No, I'm saying what we're doing currently making the linked list class is already alive.
For what you're doing currently, it's probably most closely resembles a vector, which I don't see up there. Oh yeah, yes, I'm totally blind. Okay, there are the member functions that we discussed: empty, size, top, push, pop, and their descriptions. And yeah, certainly one of the takeaways from this class, I would hope that you would pick up, is when you get out in the real world and you want to write some kind of program and you want to use some kind of data structure, you should check the STL first. STL stands for Standard Template Library. And the reason you should do this is the people that wrote the STL classes are really good computer scientists and probably did it better than you will. So use their stuff before you try to write your own. I will say that there are situations where there are things that you're trying to do as a numerical analyst or a scientist of some kind that are really unusual, and these STLs are not appropriate. They're doing something that just is inefficient for your particular application, but 99% of the time, for a mainline programmer, you want to use the STLs rather than rolling your own. Having said that, we're going to roll our own. And then after that, you can use the STLs when I say so, anyway. Okay. The the next 10 minutes, and probably into Monday, I want to talk about classes that have dynamic memory. In fact, you're dealing with such a class right now in homework with the linked list implementation. What do I mean by dynamic memory? Any program that you write that has a new command in it is using dynamic memory. Oops. What are the chances I could go back to where I was? There we go. Yeah. So classes with dynamic memory. Let's think about our linked list. So we have list, we have the public section, yada, 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 and we have the private section, which at least initially is quite simple. It's a node star. Okay, let's pretend that we're in a program and we have list A and list B. So we declare a couple of lists in the program. And then we do some stuff to B. So we do some things to B, and then we decide at some point that we'd like a copy of B. And so if you're not careful, you might do something like this. And this won't do what you want. This won't work. So you try to assign B to A. The intention of the programmer here is to take a copy of B and put it into A. What you'll get instead is let's say we've got head out here. So we've got B, and it's got its head, and that's pointing to a bunch of nodes. And what this thing will do when you copy is it'll give you a faithful, absolutely lovely copy of the head pointer. And it'll have the same address in it. And these two objects are now hopelessly intertwined. So if I start mucking around with A, I'm going to be mucking around with B. And it's worse than that. It's worse than that. Because if I try to add something to A, I'm going to get this, this, this. So now A's got some stuff of its own, and then the rest of it is from B. This is the default behavior of the assignment operator. So it'll copy all of this stuff, but the default assignment operator doesn't know about dynamic memory. So, are you stuck? No. When Strustrup wrote this thing, it was one of the first things he did. He allowed people to overload operators. So you can build, some of you may have done this with me in C++, I can't remember, but for example, you can build a set class. And you can change the plus operator so that it can take two sets and create the union of the two sets. Really cool. It's one of my favorite things about C++ is that you can build your own classes and really integrate them into the language in a nice, seamless way. And that's what's going to happen here. So we can not only overload the plus and the minus and the star and all that sort of stuff, we can overload the assignment operator. And the main reason for overloading the assignment operator is for classes, making faithful copies of classes with dynamic memory.
Generally, the assignment operator is just copying the private data from one object to the private data of another object.
Yes.
So that's what it does.
Right.
Okay.
And if you have ints and doubles and characters and strings, it's all going to be fine.
Well, even tons of structures that are basically
And structs. Right, but anything that's a pointer that's attached to some actual memory, right? You get a faithful copy of the pointer, you get your own copy of the pointer, but it's pointing at the other guy's data. That's the problem. So it can faithfully copy the pointer. What it can't faithfully do is copy the memory that's attached that pointer might be pointing at. So you have to tell it about the memory and how to copy that memory. There are lots of situations where this is a problem. So this comes up in the following situations.
Is there any way that you could use like a dereference to get it to work without having to overload the assignment operator? Because there's some fancy, I mean, or not really.
Not that I can think of.
Okay.
Not that I'm aware of.
Yeah.
So this comes up in assignment. Can you think of other places where copying happens?
I mean, the equality operator. If A equals B.
Okay, so equals equals, that's a slightly different situation because equals equals is comparing objects, but it's not responsible for creating any new objects or overwriting existing objects. But you're right, equals equals is also important. If you have equals equals and you just have lots of sort of standard variables in your private section, I take it back, still not going to work. You have to teach equals equals how to work with an overload. But that's not quite, Jamie?
I mean, I guess just with that, would it compare the two pointers? Like, so since they're not the exact same pointer, no matter what you ever do, they're never going to be equals equals?
I have to think about what would happen if I compared.
Because like if you just did A equals B without overloading the assignment operator, and then you did A double equals B, would it return true?
I have to think about that.
Okay.
The thing I'm concerned about is I can think of two possibilities. Either it's always going to be not equal, or it's actually smart enough to go look at the memory footprint of the private variables and actually compare all those memory locations side by side and do the right thing. I suspect that it's not that smart. In any case, when you're dealing with comparing objects, you always want to write a comparison operator, because think about the things that you can compare. I mean, usually it's doubles and ints and that sort of stuff, and there's sort of a natural notion of what you mean by compare. But when you have an object with lots of stuff in it, then all bets are off, right? What do you mean by equality? Maybe you just want the size to be equal, or maybe, so I suspect that it just doesn't work.
Yeah.
It'll just say equals equals is not defined for lists. It'll be a compiler error or something, but test it. Okay, so, but where else do we have to make copies of objects? Function calls by value, right? Function calls by value. And the third one is really, I'd be impressed if somebody got this.
Isn't it addition? Is it like having to do with how it evaluates the size of the expression?
If you write your copy constructor, so let's say you overload the addition operator. You're perilously close, actually, to this third case. Anybody know exactly what the third situation is? When you return an object. And I'm going to say return by value. Yes.
Is that just by using the new pointer?
And we're going to talk about return by reference because it's important to writing assignment operator overloads. Return by reference, because one of the things that Josh is familiar with is when you do A equals B equals C, it actually works. And the reason it works is because B equals C does what? Do you know, Josh? I don't want to put you on the spot. Do you know what happens when you do, so you have A equals B equals C all in one line, semicolon.
B is set to C and then A is set to B, right?
What's actually happening?
Well, it's running two functions, right?
It's
It
running
runs them
equality.
from right to left.
It's running assignment from right to left, and when you do B equals C, you may not know this. When you do assignment, the return value of the assignment operator is the right-hand side. So B equals C does the assignment, and then it returns C. So now B equals C turns into C, and now you have A equals C. And then that's going to return C also, but it doesn't care. It goes off into the ether. And this lets you do recursive assignments like that. A equals B equals C equals D equals, right? Another operator that does that is the insertion operator. When you do the insertion operator, you always return the right-hand side by reference. And that's so that you can string the double less than thing. Right? So you can string a whole bunch of things together with double less thans. And the reason that works is you evaluate it, and then it returns a C out. And then and this goes from left to right, but it's a similar idea. So you do the first one, it returns C out, that collapses into C out, then it's ready for the next one, collapses to a C out, it's ready for the next one. Jamie?
Just really quick, the less than. So if you have just one less than 2, then that would return a Boolean, right?
Yes.
And then if you have a big string of them, it doesn't return Boolean and then a Boolean. And
Right, because it doesn't make sense.
Right.
Right.
But so it just knows that and figures it out.
There's no comparison between a Boolean and an integer.
Right.
Then, so it just doesn't run it or.
So there's no return. It just wouldn't make sense, right? So if you did A less than, like a really common programming error is somebody wants a number to be between 1 and 2.
Right.
And so they do 1 less than X less than 2.
Yeah. Okay.
Right?
I just thought that's what you were saying with that.
And so the compiler error you're going to get there is along the lines of what Josh was just saying. It'll say try to do 1 less than X. The compiler will see that that's going to turn into a Boolean, and then it's going to say, oh, Boolean less than 2, and it's going to say, I don't know how to compare Boolean and 2, and it's going to not compile. So there are copy constructors and assignment operator overloads. I'm going to talk about this on Monday, how to write an assignment operator overload, and then that's actually the more complicated of the two. And then you'll use the assignment operator overload to actually do your copy constructor. And each of these has a very specific syntax that you have to follow in order for the program to use them correctly. That's what we'll do on Monday. Have a good weekend.